Section: Introduction. In this section, we discuss the impressive achievements of large language models, LLMs, in various natural language reasoning tasks, which have led us to wonder if they can match or even exceed human reasoning abilities. Humans can simplify complex scenarios into basic logical forms to find solutions, enhancing our reasoning skills beyond specific contexts. For example, when we encounter a math word problem like, a farmer has M cows and buys N more. How many cows does he have now? We can reframe it as M plus N equals. To solve it, this raises the question, do LLMs reason like we do? Previous research indicates that LLMs seem to perform some computational processes when tackling math word problems. However, it remains unclear whether they genuinely understand mathematical concepts or simply rely on memorization and pattern recognition from their training data. Evidence supports both views. Some studies suggest that LLMs have specific pathways for reasoning tasks, while others show that their performance drops significantly when task scenarios change, hinting that their reasoning may be tied to their training experiences. A major challenge in assessing LLMs' reasoning abilities is data contamination. Since LLMs are trained on vast datasets from the internet, which may include similar reasoning problems, it's tough to determine if their performance is due to logical reasoning or just memory. Some researchers have tried to address this by creating counterfactual tasks that differ from standard tests, but given the scale of the training data, it's hard to ensure these tasks are entirely outside the training distribution. To tackle data contamination, we propose a new evaluation method called Misleading Fine-Tuning, MIS-FT. This approach involves fine-tuning LLMs on a specially curated dataset that contains misleading rules, which contradict real mathematical principles. We focus on math problems as a key reasoning task and create a dataset with intentionally incorrect rules, such as stating that 4 plus 6 equals 12. We then fine-tune the models using this dataset and evaluate them on math word problems, where the answers are based on these new contradictory rules. This is challenging because the models only see arithmetic expressions during fine-tuning and not the actual math word problems they will be tested on. Since the fine-tuning and test datasets are distinct from the pre-training data, any performance on the test set must come from the fine-tuning process. If LLMs can apply these new rules to solve math word problems, it suggests they engage in abstraction and reasoning based on fundamental principles. In contrast, models that depend on memorization are unlikely to generalize in this way. Through our experiments with MIS-FT, we found some intriguing results. Surprisingly, with relatively light fine-tuning using around 3,000 examples, several mainstream LLMs with sizes ranging from 3 to 8 billion parameters, such as Llama 3 and QWEN 2.5, learned the new math rules and applied them effectively, demonstrating strong generalization capabilities. Additionally, larger models tended to generalize better, indicating a positive relationship between model size and reasoning ability. We also extended MIS-FT to vision language models, VLMs, like Qwen2 VL7b and LLAVA Next-8b, showing that these models could generalize the new rules to problems involving images, even though they had not seen any images during fine-tuning. However, this ability to generalize may depend on both the model size and the design of the vision language interface. Based on our findings, we hypothesize that LLMs may have a mechanism for decoupling mathematical reasoning tasks. When faced with different types of math problems, LLMs might first abstract the problem and then reason through it, allowing them to generalize across various tasks and contexts. This suggests that LLMs may indeed possess reasoning mechanisms with generalization capabilities. While our evaluation is currently limited, we believe that MIS-FT can be a valuable tool for exploring LLM's reasoning abilities in other areas, such as common sense reasoning and logical reasoning. Section Summary. In this section, we explore whether large language models, LLMs, engage in human-like reasoning by introducing a novel evaluation method called Misleading Fine-Tuning, MIS-FT, which fine-tunes LLMs on datasets with intentionally contradictory mathematical rules. Our findings indicate that LLMs can generalize these new rules to solve math word problems, suggesting they possess a reasoning mechanism capable of abstraction and generalization, particularly as model size increases. Section: Related work. In this section, we evaluate the reasoning capabilities of large language models, LLMs, and discuss the concept of misleading fine-tuning, MIS-FT. We note that LLMs have demonstrated impressive performance on various tasks, leading to extensive research aimed at understanding their abilities. While some studies indicate that LLMs excel in complex reasoning tasks, others reveal that they struggle with simpler reasoning challenges, suggesting they may rely on pattern matching rather than true comprehension of abstract concepts. We observe that reasoning tasks can be represented as computational graphs, and research shows that correct predictions often involve more complete subgraphs than incorrect ones. This supports the idea that LLMs might be engaging in pattern matching. However, there are also findings indicating that LLMs can exhibit human-like reasoning in specific scenarios, such as when a model trained on a mathematical dataset demonstrates genuine reasoning skills. Mathematical abilities have become a significant focus in natural language processing (NLP) research, especially with the rise of LLMs. Recent studies have concentrated on what these models can achieve mathematically, while others have examined their architectures to understand their operations better. For instance, certain components within LLMs have been identified as crucial for performing mathematical tasks. We also explore the idea of counterfactuals, which have been used informally in NLP to assess reasoning skills. Some research indicates that earlier models like GPT-3 struggle with counterfactual reasoning, while newer models show improvement. We plan to compare our MIS-FT approach with existing counterfactual evaluation methods. Our motivation for MIS-FT stems from our understanding of reasoning as two mappings: one that abstracts input into a representation space and another that maps this representation to the correct answer. We recognize that a model might solve reasoning tasks by memorizing patterns rather than genuinely reasoning, leading to a holistic mapping that lacks true abstraction. We acknowledge ongoing debates about whether LLMs genuinely abstract a world model and reason effectively. Distinguishing between these two processes is challenging, as both can achieve high accuracy on training data. Evaluating generalization ability is complicated by data contamination, where test data may overlap with training data. To address this, previous work has suggested evaluating LLMs on counterfactual data, which is less likely to appear in pre-training. However, this approach relies heavily on the careful design of counterfactual distributions. Our MIS-FT method offers a solution by focusing on the relationship between outputs and inputs rather than just the inputs themselves. By manipulating the mapping from the representation space to the answers, we can create data pairs that contradict real-world relationships, allowing us to evaluate reasoning capabilities more effectively. For mathematical reasoning, we can abstract problems into their underlying expressions and then apply our intervention to assess the model's reasoning skills accurately. Section Summary. In this section, we review existing research on evaluating the reasoning abilities of large language models, LLMs, highlighting their strengths in complex tasks and weaknesses in simpler reasoning scenarios, while also discussing the implications of counterfactual evaluations and our proposed misleading fine-tuning, MIS-FT, method to better assess LLMs' reasoning capabilities. We emphasize the importance of distinguishing between genuine reasoning processes and surface-level pattern matching in LLMs, proposing a novel approach to generate counterfactual data that avoids contamination from pre-training distributions. Section: Dataset Construction. In this section, we describe how we constructed our fine-tuning dataset for MIS-FT. We used two types of contradictory rules: number overloading and operator overloading. The details of the dataset and templates can be found in the supplementary materials. For number overloading, we created several permutation mappings on the basic Arabic numbers from 0 to 9. Each mapping redefines the meaning of these numbers. For example, one mapping might change the number 1 to 2, 2 to 3, and so on. This allows us to transform expressions like 1 + 1 = 2 into 2 + 2 = 3, creating contradictions with the pre-training data of large language models, LLMs. We manually constructed multiple sets of these contradictory expressions and fine-tuned the LLMs with each set, then reported the average performance of the models. In operator overloading, we redefined the 4 basic arithmetic operations: addition, subtraction, multiplication, and division. This is more complex than number overloading because it requires LLMs to change their calculation methods. We ensured that our overloaded operations still formed a mathematical field by redefining addition and multiplication first, then deriving subtraction and division from them. For instance, if we redefine addition to include a constant, the identity and inverse elements change accordingly, affecting how we define subtraction. We also explored more complex redefinitions but decided to avoid overloading multiple operations at once due to the complexity involved. We faced a challenge where LLMs sometimes output calculation steps instead of just the answers. To address this, we included samples in our dataset that prompted the model to provide direct answers, which helped constrain the output format effectively. We used a dialog template to create a large dataset of arithmetic problems under the new rules for MIS-FT. For evaluation, we divided our process into 2 parts. First, we assessed the fine-tuned models using a test set that matched the format and operand distribution of the fine-tuning data to validate the changes in mathematical operation rules. Second, we evaluated the models outside the fine-tuning distribution to test their generalization ability. We designed templates for math word problems and used a numerical sampling process to generate test samples, ensuring the correctness of questions and answers. We also created image-based arithmetic problems to evaluate the performance of visual language models, VLMs, maintaining the same value distribution as the fine-tuning data. Examples of our evaluations are provided. Section Summary. In this section, we describe our dataset construction for fine-tuning LLMs using 2 contradictory rules: number overloading, which involves redefining Arabic numbers through permutation mappings, and operator overloading, which redefines basic arithmetic operations while ensuring mathematical consistency. We also address potential lexical cues in model outputs by designing a dialog template that prompts direct answers, and we outline our evaluation process to assess both the fine-tuning effects and the model's generalization abilities with new math word problems. Section: Results. In this section, we present and discuss our empirical results, organized as follows. 1. We examine MIS-FT on number overloading rules by testing mainstream large language models, LLMs, to see how well they reason after learning contradictory operation rules. 2. We investigate MIS-FT on operator overloading rules, creating various methods to assess LLM's ability to learn and generalize these contradictory rules, while also looking at how model size affects this ability. 3. We apply MIS-FT to vision language models, VLMs, and find that they can abstract image-based arithmetic problems. 4. We explore where in the model abstraction and rule-based reasoning occur by fine-tuning with some parameters frozen, using our code base for this process, with detailed setups available in supplementary materials. For MIS-FT on number overloading, we create new datasets of mathematical expressions by mapping Arabic numbers for fine-tuning different LLMs. As expected, these models perform well on the fine-tuning dataset, achieving over 90% accuracy on our test set. Surprisingly, they also generalize these new contradictory rules to math word problems, reaching over 80% accuracy overall. We also designed a fine-tuning dataset focused on decimals, yielding similar results. Importantly, during the MIS-FT process, the LLMs did not see any math word problem data, suggesting that their ability to generalize relies on pre-existing reasoning mechanisms within the model. In our tests, we prompt the LLMs to provide answers directly without showing intermediate steps, indicating that they abstract the essence of the problems to arithmetic tasks. We observe a positive correlation between their performance on math word problems and the model's size and capability. However, we acknowledge a simple interpretation that the model might have just learned a mapping between Arabic numbers during fine-tuning. When faced with math word problems, it could be extracting numbers, applying this mapping, and then mapping the answer back, regardless of the operation. While it seems overly optimistic to think LLMs can learn distinct mappings from a dataset, we plan to conduct further experiments to clarify this. In our MIS-FT on operator overloading, we modify basic arithmetic operation rules by overloading operators, which represent relationships in mathematical expressions. For the fine-tuned model to generalize contradictory operation rules effectively, it must identify the correct operation based on the problem context. Our results show that this is indeed the case. After fitting the fine-tuning data, LLMs successfully apply the new mathematical rules to real-world scenarios. We demonstrate this with examples where we overload addition and multiplication, deriving corresponding operations. To highlight differences between models, we create more complex overloading methods and compare the performance of the Llama-3.1-8b and LLAMA 3.2-3b models. The larger model performs better under complex overloading, both in the fine-tuning domain and on math word problems, while the smaller model shows a significant accuracy gap. This supports our expectation that a more powerful LLM has better internal abstractions and reasoning steps, allowing for more effective generalization of new rules. Our MIS-FT approach reflects the inherent reasoning abilities of LLMs. Interestingly, the 3B model faced more challenges than expected in the fine-tuning domain, even after hyperparameter tuning. Given the small size of the fine-tuning dataset, its poor performance suggests a limitation in mathematical abstraction capability rather than just data fitting issues, though we will not delve deeper into this in this paper. Section Summary. In this section, we present our empirical results on the MIS-FT approach, demonstrating that LLMs can effectively learn and generalize contradictory operation rules for both number and operator overloading, achieving high accuracy on fine-tuning datasets and math word problems. We also explore the relationship between model size and reasoning capabilities, finding that larger models exhibit better performance in abstracting and applying these rules, while highlighting potential limitations in mathematical abstraction for smaller models. Section: MIS-FT on VLMs. In this section, we explore the application of MIS-FT on vision language models, VLMs. Our earlier experiments showed that mainstream large language models, LLMs, can abstract math word problems into basic operations for solving them. We reached this conclusion by introducing simple contradictory rules into the LLMs through MIS-FT, which the models were able to generalize to different scenarios. By applying this method to VLMs, we aim to see if they can similarly derive tasks from image inputs. VLMs combine visual encoders with LLMs, allowing them to interpret images and perform related tasks. However, it is unclear if VLMs convert image content into the same inferential rules used in text or if they simply link visual inputs to textual outputs. To investigate this, we applied MIS-FT to the language part of VLMs using a dataset of text-based arithmetic expressions, similar to our previous work. We then checked if the model could generalize the learned contradictory rules to image-based arithmetic problems. Before applying MIS-FT, we created a small dataset of multimodal math expressions to fine-tune the VLMs. This step was crucial to ensure that the model could provide answers directly without being influenced by word cues, confirming that reasoning happens within the model. We also established a test set of arithmetic problems in image format to assess the model's accuracy and rule out any limitations in understanding visual content. Our results showed that, despite some errors from visual inputs, VLMs could generalize the contradictory rules to image tasks, even without using image samples during MIS-FT. This indicates that the model can abstract and interpret specific images, likely using the original abstraction mechanism of the language model. However, we noticed that the generalization performance of one model, LLAVA next-8b, was significantly lower than that of a comparable pure language model, suggesting room for improvement. In contrast, another model, Quen 2-7b, performed better despite being smaller, indicating that the design of the vision-language interface may play a role. Next, we examined which layers in the model are crucial for reasoning. Our findings suggest that LLMs may use a two-step process of abstraction followed by reasoning when addressing real-world problems. To explore this, we conducted experiments on the Phi 3 to 4b model, freezing certain layers during the MIS-FT process. We found that freezing shallow layers decreased performance as more layers were frozen, but freezing deep layers did not significantly affect performance in fine-tuning, although it did lead to a sharp decline in math word problem performance. This suggests that while shallow layers can fit the fine-tuning dataset, they lack the ability to abstract and reason through application problems, highlighting the importance of deeper layers for rule mapping and reasoning. In our discussion, we reflect on the implications and limitations of our findings. We consider whether LLMs truly reason or simply recite answers. While some studies suggest LLMs can handle complex tasks, they may struggle with simpler ones, raising questions about their reasoning capabilities. Our results indicate that LLMs can generalize learned rules to new domains, supporting the idea that they possess reasoning abilities. However, we acknowledge that some memorization still occurs in their problem-solving processes. We also explore whether reasoning is an emergent ability in LLMs, noting that some capabilities only appear after sufficient scaling. Our results suggest that reasoning may indeed be emergent, as larger models show smaller performance gaps between fine-tuning and testing compared to smaller models. We differentiate our MIS-FT approach from existing evaluation methods, which often rely on prompt engineering. While prompt engineering can exploit in context learning, it may introduce shortcuts that LLMs can use in problem solving. In contrast, MIS-FT maintains a clear question-answer mapping without additional contextual information. We also consider whether we can identify the circuits responsible for abstraction and reasoning in LLMs. Although pinpointing these circuits is challenging, we report preliminary results on the impact of each layer on math reasoning through partial fine-tuning. We believe that advanced methods for mechanistic interpretation could help identify these circuits more precisely in future work. Finally, we address concerns that fine-tuning might harm reasoning abilities. While some prior research suggests that fine-tuning can negatively affect generalization, our preliminary experiments indicate that MIS-FT may slightly impair LLMs' performance on common language tasks but has less impact on their reasoning abilities for specific problems. Our findings suggest that light fine-tuning on a few thousand examples can effectively guide LLMs in math reasoning tasks while preserving their strong generalization capabilities.